Hello there. In this lesson, we're going to learn about static electricity that can be produced without any contact between objects or substances. This process is called induction. And also there are moments when you can see static charge moving all at once from place to place without contact as well, which we'll look at the end, which is discharge, which is kind of what you're seeing here, where there's electrons moving so rapidly that they heat up the air so it glows and you can see it, which is really neat. So induction, being the fancy word for charging something without actually touching it, is what we saw way back at the beginning when we were looking at charge separation, how objects can be charged just by being close to another charged object. And so the example of the can is that the can doesn't have any charge at all, but because the balloon here has been charged, let's say the balloon has a negative charge here from rubbing against someone's head, these negatives in the balloon will push the negatives in the can away. So there'll be negatives over here because they're repelled from that balloon. And of course, when you remove negatives from one side of the can, that means that side of the can will get a positive charge because it lost a few of its electrons, at least temporarily, while they move to the other side of the can. And so that's why there's attraction overall, and the can will follow the balloon. It's kind of neat. If you haven't seen it, try it out at home. Another thing you can try out is if you charge up something by static electricity, you can bring it close to a stream of water. This also has the same effect of causing attraction, which is because of a charge being induced on the water. So normal neutral water, of course, will fall, out of a tap, right, in the wall, and it'll go straight down. But if you bring an ebonite rod, or say like a plastic comb that you've been running through your hair that has a charge on it, you'll see that flow of water will be attracted to the rod, right? It'll bend over. It's kind of neat. It's like magic. If you're lucky to have one of these ebonite rods, it's kind of like your Harry Potter. You'll be attracting the water from a distance. It's pretty neat, so give it a try. The opposite effect, of course, is if you have a positively charged rod rather than a negative one. And we know that you can make a positively charged rod by rubbing glass on some silk. And so if you have a positively charged rod, a few negatives in here, but more positives, you might be a little confused to see that the same attraction takes place. You'll have this flow of water that changes its course to get closer to the glass rod. And of course, it'll sputter down at the bottom here. But there will be some attraction there as well. So how do you get attraction with both positive and negative? Well, it's the opposite effect of having a charge separation. So if these are all positively charged, this is going to attract the negative part of the water molecules to this side, and you'll get attraction. With the ebonite rod, it was just like the balloon example where the negatives were repelled, and that left the side closest to the rod positive, and again, you get attraction. So it's attraction either way by induction because it induces the opposite charge. Okay, on an electroscope, you can also see the induction in action. If you bring your negatively charged ebonite rod close to the electroscope but don't touch it, you'll see that the leaves at the bottom move away from each other. So that means the electroscope is getting charged, but nothing has touched it yet. Same thing with a positively charged glass rod. If you bring that one close, you'll also see the leaves move apart. So in both cases, there is a charge being produced down here on these leaves, but it's the opposite process in each one. With the negatively charged ebonite rod, it's going to push electrons away from the rod down into these leaves, and the leaves will have a temporary negative charge, and you'll see the leaves separate from each other. With a positively charged rod, that's going to attract electrons up into the top here. And if you attract electrons up, then what's left behind down here is going to be positive, and you'll have that repulsion again. So a neat thing can be accomplished as well, where you can give the electroscope a permanent charge without having it contacting the charged object. So start again with your ebonite rod with its negative charge. And if you bring that close to your neutral electroscope, this time, to make it a little different, you're going to connect the electroscope to the ground. The symbol here is for ground. So let's, you can just touch it, right? So if that's just represent your finger, let's be your arm. Let's draw a head here. Yeah, you're standing on the ground. There you go. There's your other, yeah, so you got Mr. Fantastic arms, so you can stretch them out there, touch the electroscope, and this time, instead of the electrons going down into the leaves of the electroscope, the electrons will leave the electroscope and go through your body and into the ground. Well, that's great. They've left the electroscope. Now, that means the electroscope will have a positive charge because you've lost some of the electrons. So in order to give it a permanent charge, what you have to do is let go, disconnect from that electroscope, and now it'll have a permanent positive charge. And even though you did touch it with your hand, you didn't touch it with anything charged, and so you could still say that the charge was given by induction. Finally, a little bit about grounding and other movements of electrons. We just went over the symbol there, so symbol for grounding, if you're going to include it on an electrical diagram, is these three horizontal lines. If you have a plug in your home that has this third tine on it, that's also for grounding. It'll be attached to the box, which is attached to the house, which is attached to the ground inside of your home. And the reason for grounding is often for safety's sake. It's a place for excess electrons to either be absorbed or released back into the ground. So grounding works with any large objects. Of course, the Earth is the biggest object, and so it works really well. You can think of it as a reservoir that can always absorb or give off more electrons as needed in order to neutralize any object. So if you touch a charged object, it can be neutralized by attaching it to the ground. Right? So our last little topic here is about when electrons move all at once from one place to another. And that's sort of what we started with at the beginning of this lesson, with that image of the little lightning bolt jumping across the Windhurst machine. So what happens is that when there's a large buildup of electrons, or positive charge either way, electrons can be attracted or repelled so that they move sort of all at once when there's an opportunity. And when it does this, that's called electrical discharge. And so anytime you see, maybe when you're taking your sweater off and you see little sparks inside there as your shirt rubs against your sweater, those are little tiny electrical discharges where electrons are jumping and trying to neutralize a charge when there's a difference. You might have rubbed your feet on the carpet like this little app. If you type John Travoltage into Google, you'll get this neat little application where you can charge up his body by rubbing his foot against this wool carpet, and you'll see the electrons build up and build up and build up, and then you can move his hand over close enough to this doorknob and you'll get this big electrical discharge. The other place, of course, that you see it is with lightning, and that process is a little more involved, so we'll do it on the next slide. Yes, lightning. So lightning is also the result of friction, where different particles of different substances bump into each other and produce a static charge inside of clouds. So you start off with friction, where inside a cloud here you got a lot of like dust building up, and what tends to happen is that the bottom side of clouds ends up with a negative charge. So you end up with a negative charge at the bottom side of clouds. And then because there's so much of this charge, it can act as an induction to the ground below. So if this is all negative, that means that the electrons at the surface of the ground will be repelled away, and that'll produce a surface underneath the cloud that is kind of positive. So the stage is set here for some serious attraction between the negative charge of the cloud and now this positive charge that has been generated or induced below. So once that happens, the electrical discharge can occur where electrons hop from like air molecule to air molecule in this sort of crooked pattern and eventually end up at the positively charged Earth. It can also happen between clouds. If there's like a positive side of one cloud, and you can get bzz, 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 going across from cloud to cloud, or it can happen within a cloud. You can see electrons jump from where there's lots on one side of a cloud to lots on the other side of the cloud. You might have seen that looking up in the sky. You can see lightning going back and forth up there, but not hitting the ground. Finally, a little bit of protection that you might see if once you know about it. Tall buildings around can have these little spikes on the top of them that act as a protection to the buildings themselves. Now, it happened in the past that our buildings were built primarily of wood, and if they got struck by lightning, that would cause, a fire, right? That'd be bad, especially if it was a barn full of hay and cows and that sort of thing. Big loss and bad news. So a little bit of interesting technology is to put a lightning rod, like a high piece of metal sticking up above the highest point of the building. And then if the lightning strikes, the electrons, instead of going through the building and lighting it on fire, they'll follow a wire around the outside of the building and then safely into the ground. So that bit of technology saved a lot of barns and a lot of people from fires.